For this exercise, we're going to look at three aspects of matrices. The first is determinant of a matrice, then we'll look at the inverse of a matrice, and then we'll look at what it means for a matrice to be singular. So the first aspect, so for every square matrice or matrix, we can assign a value called the determinant. Now we'll use the Greek symbol or Greek capital letter delta again, so that's the triangle. It's exactly the same symbol that we used when we were looking at derivatives. No correlation between derivative and determinant here. It's only because they both begin with D that we use the symbol delta. If we have a square 2 by 2 matrix, so for instance this particular matrix here, A equals A, B, C, D, we can evaluate the determinant of A in the following way. So the determinant of A, called dA, which is the same as using the Greek letter delta. You can also write the determinant as A with two straight bars around it, or we can just put the two straight bars around the matrix array, and all four of those representations are just different notations for writing determinant of A. So the way in which we calculate it, all that we do to calculate the determinant is to take A and multiply it by D, and then subtract B multiplied by C. So the determinant of A is just equal to AD minus BC. It's that simple. So this is the important bit that would go in a summary book. So an example, if we're asked to calculate the determinant of this matrix B, you can write the symbol for the determinant, which is of course the same as if I write the determinant in this fashion. And that is just equal to 3 times 5 minus 2 times 4. So paying special attention there to the negatives. So I've got A times D minus B times A, where B is actually negative 2, not B times A, B times C. 3 by 5 is 15, minus 8, so it becomes plus 8, which is just 23. So a second example here. Given that the determinant of A is 0, and that we have the original matrix A equals 3, 2x, x, 6, we need to find the value of x. So we use the information that's given. The determinant of A is equal to 3 times 6 minus 2x times x. So that's just 18 minus 2x squared. And we're also given the information that the determinant of A is equal to 0. So in other words, 18 minus 2x squared is equal to 0. So now we just have to solve this equation for x. So we have minus 2x squared equals minus 18 if we subtract 18 from both sides. dividing both sides by -2 gives us 9. Find the square root of 9. Don't forget the square root has a minus or a positive, so it's plus minus square root of 9, which is 3. So we have two solutions or possibilities for x. So how would we find the determinant on CAS? So if we use that same, we do or use a square matrix. So if we use the matrix that we used before, which was 3 minus 2 4 5, we can store that matrix. Control store, we'll call it A. Now if we want to find the determinant, if we go to menu, there is a matrix menu, and you'll see there that one of the options is to calculate the determinant. So we can calculate the determinant of A, press enter, and it'll tell us it's 23, which is what we worked out here. You could in fact calculate the determinant without storing it. So you could just calculate the determinant. Oops, we need determinant and then enter the matrix straight into there. Oops. Press enter and it would still calculate it exactly the same way, but we didn't have to store it in that instance. So now pause, just have a go at questions 1 and 2 from 7.4. They're both related to determinants before you go on to calculating inverses. So to calculate the inverse of a 2 by 2 matrix, hopefully by now you've completed the 7.3 questions, and you will have seen that multiplying a square matrix by the same sized identity matrix gives back the original matrix. So what I mean by that is if you have some matrix A, you multiply it by the identity matrix, you just get back whatever A was originally. So for example, if we have this matrix here, 3, 7, 2, 1, and we multiply it by the same sized identity matrix. Remember, the identity matrix is a matrix where the diagonals from left to right are 1s, and then all other values in the matrix are 0. So if we multiply this, it means we have to multiply this top row by the first column here, so that we have 3 times 1 plus 7 times 0. Then we multiply the 3 by 7, 3 and 7 multiplied by the second column, the second matrix. So we're going to multiply by this column this time, so that we have 3 by 0. We're going to add 7 times 1. Continue that multiplication pattern so that we multiply the second row by the first column, so that we have 2 times 1 plus 1 times 0, and then lastly the last row by the last column, so we have 2 times 0 plus 1 times 1. And when we evaluate that, 3 times 1 is 1, plus 0 times 7 is just 3. 3 times 0 is 0, plus 7 times 1, which is 7. 2 times 1 is 2. 2 times 0 plus 1 times 1 is 1. And we just get back that exact same matrix. Same. So inverse, the inverse of a square matrix is related to this concept. So the inverse of a square matrix of A is a second matrix, and we denote that A to the -1. So you remember from things like when we were doing sine of theta, that the inverse of sine of theta, we write it like that. sign -1. Similar sort of notation. So if we have a square matrix A, an inverse of that matrix is A to the -1. So the rule here is that if we multiply A by its inverse, we get back the identity matrix. So it's similar to this concept above. So here we multiplied A by the identity and we got back to A. Here we're going to multiply A by its inverse and we're going to get the identity matrix. So that rule is that the inverse of a matrix A is a matrix A inverse, such that if I multiply A by A inverse, I get back the identity matrix. So in this example, we want to show that the inverse of the matrix A is A to the -1. We're given A and we're given A to the -1. So potentially, if we multiply these two matrices together, we should get back to the identity matrix if A to the -1 is the inverse of A. So I've got a 2 by 2 times a 2 by 2, so we should get back a 2 by 2. So first row of the first matrix times the first column of the second matrix. So we have 2 times a half minus 1 times 0. Next value, we take the first row of the first matrix times the second column of the second matrix. So we have 2 times a half minus 1 times 1. Next value, we take the second row times the first column. So we have 0 times a half plus 1 times 0. And finally, the last row times the last column, 0 times a half plus 1 times 1. If we evaluate that, the first value becomes 2 times a half is 1, minus 0 is just 1. The next value, 2 times a half, is 1, minus 1 is 0. Next value, 0 times a half is 0, plus 0 is 0. And lastly, 0 times a half is 0, plus 1 times 1, which is just 1. And we get the identity matrix. So we'll just conclude that with a little comment, as desired. So if we're asked to find the inverse of a 2 by 2 matrix, we can use the rule below. So that rule says that if we've got a matrix A equals A, B, C, D, then the inverse is equal to 1 over A times D minus B times C. And we multiply that by sort of a rearranged version of the original matrix. So we swap A and D and we make C and B negative. If you also notice that this value that's underneath here, AD times BC, that's in fact the determinant. So what we learnt to calculate previously was that the determinant was AD minus BC. And that comes out in this relationship here. So we can also write it as 1 over the determinant times D minus B minus CA. So an example, we're asked to find the determinant of this matrix here. A equals 1, 0, 4, 2. We find the inverse. The inverse is equal to A times D minus, oops, what am I doing? It's equal to 1 over A times D minus B times C multiplied by D minus B, which is minus of 0, which is just 0, minus C, which is minus 4, and then A, which is 1. So evaluating that becomes 1 over 2. 1 times 2 is 2, minus 0, so we're just left with 2 there. So it's a half times 2, 0, minus 4, 1. Now we can leave it like that, or you can multiply through. This is just scalar multiplication, right from exercise 7.2. So we just take that scalar that's out the front and multiply it by all the values which are inside the matrix. So half of 2 is 1, half of 0 is 0, half of minus 4 is 2, minus 2, and half of 1 is just a half. Now, an important note here is that we previously discussed the importance of the order of multiplication with matrices. Inverse matrices are an exception to the rule. It doesn't matter which order we multiply A times A inverse or A inverse times A. Either way, we still get the inverse matrix. The identity matrix. So how do we do that on the CAS? We can either store our value for A. So let's do a new matrix here. Whoops, remove all that. Sorry, we're going to store our matrix in there, and the matrix that we used for our example was 1, 0, 4, 2. We'll store that as A this time. Control, store A, a new A value, and if we want to find the inverse, all we do is write A, use the hat button, and write -1, and that should calculate our inverse, which is exactly what we calculated manually. Again, you don't have to store it. You could just use that value and write hat -1 without storing A, and we should get exactly the same value. So pause again. Try the questions that are related to inverses. So that's just questions 3 and 4 and 9 and 10. There's just a little bit to add. So we have this fact that if a matrix has a 0 determinant, then the inverse matrix does not exist. So we call the original matrix, in that case, a singular matrix. So if we think about it, we know our rule for the inverse looks like this. We know that the value underneath the 1 here is the determinant. So if the determinant was equal to 0, then we'd have that A inverse is equal to 1 over 0. And we should remember that 1 divided by 0 is undefined. So therefore, if the determinant is equal to 0, then the inverse matrix cannot exist. So then the original matrix A would be called singular. So if we ask to show that this matrix here is singular in the example, all we have to do is show that the determinant is equal to 0. So if we find the determinant, we'll call that matrix A. Determinant of A is equal to 3 times 6 minus 2 times 9, which is equal to 18 minus 18, which equals 0. We write some statement as the determinant of A equals 0, the inverse of A does not exist. Therefore, A is a singular matrix. So lastly, a few more questions to answer. So just try questions 5 and 6. 13, 14, 15, they're the challenging ones, but it shouldn't be any trouble if you use them with the solutions manual.